Hello friends, I welcome you in lecture number 33 on graph theory. In this lecture we are going to understand the meaning of rooted tree. What is a rooted tree and how we can construct rooted tree from given tree. So rooted tree is a special type of tree in which one vertex is designated as root and every other vertex is positioned by its relationship with that designated vertex as a root. So rooted tree is a tree in which one vertex will be considered as root and every other vertex is positioned by directed edge which is away from that root. So first we understand with the help of this tree and we see how we can construct rooted tree from this unrooted graph of a tree. Suppose I consider this root A, this vertex A as a root for my rooted tree, then I will put this vertex A at the top or bottom of the graph. Generally we will consider our root at the top of the tree. So first I am considering a rooted tree in which I designate this vertex A as root of the rooted tree. Now A is adjacent with this B, D and C. So I can put arrow from A to this B, D and C. So here I am writing B, then it is adjacent with B, D and C. So here I am writing D and C. So here I write, suppose I write D here, then B, C and D, and we can see A is adjacent with B, C and D. So we are putting this directed edge from A to B, from A to C and from A to D. Now we check that these three vertices B, C, D are adjacent with which vertices. So B is adjacent with these two vertices F and G. So below B I will put this F and G and I will direct them by an arrow. From B I have two directed edges towards F and G. C is adjacent with only one vertex E. So here I am writing E here and I will consider directed edge from C to E. So here I am writing E and D is not adjacent with any other root. So I will keep this as it is. So you can see here I have 1, 2, 3, 4, 5, 6 and 7 vertices. So let me count here 1, 2, 3, 4, 5, 6 and 7. So this is the rooted tree in which we have considered this vertex A as root and all other vertices are positioned by their relationship with this root vertex A. And we know that in a tree there is a unique path between any two vertices. So this type of relationship always will be there, and because of this definition of tree we can go from root to every vertex by a unique simple path, and we can go from vertex to the root by a unique simple path because we are considering a tree and we know that in a tree there is a unique simple path between any two vertices. So in this way we can construct a rooted tree. We have to consider any one vertex as root and then we will put this type of directed edges by the position of other vertices with respect to this root A. Now different choice of roots will give us different rooted trees. This is rooted tree with A as a root If I wish, I can construct another rooted tree with C as a root. Suppose I consider C as a root. Let me put C here. Then here I am writing C. Now C is adjacent with A and E. So from this I will have two edges directed towards A and E. So let me write A and E here. This is for A, this is for E, and I am considering arrow. And it is not necessary to consider directed edge. If we wish, we can ignore this arrow also, because we know that in a tree there is a unique path between any two vertices. So from C I have two vertices which are adjacent with C, which are A and E. Now E is not adjacent with any other vertex, so we check for A. A is adjacent with D and B. So here I have to consider D and B. So suppose I consider D and B here. Suppose I put two vertices somewhere here. A is adjacent with B and D. So let me put B here and D here. And I have to consider this direction. A is adjacent with B and D. Now we can see D is not adjacent with any other vertex, but B is adjacent with F and G. So below this B, again I have to consider two vertices, and which are F and G. So here I am writing F and G, and I will consider this type of directed edges from B to F and from B to G. So this is another root in which we have considered vertex C as a root. So this is also a rooted tree with C as a root. So in this way we can construct a rooted tree. Rooted tree is a special type of tree in which one vertex is designated as a root and other vertex are positioned with respect to their relationship with root. So sometimes they can ask you to write down the definition also. I have written definition here. A rooted tree is a tree in which one vertex has been designated as the root and every edge is directed away from the root. Here we can see that every edge is directed away from the root because we have taken roots at the top of the graph. If we wish, we can consider roots at the bottom of the graph also, but in this course we will consider roots at the top of the graph. Now we have some terminology related to this rooted tree. From rooted tree we can define certain terminology by the position of vertices with respect to the root. So here I have taken one root in which I have not put arrows on the edges. If we wish, we can ignore these arrows also, because in a tree there is a unique path between any two vertices. Now we try to understand some terminology related to rooted tree. Here we can see that A is at the top and it is our root for this rooted tree. Now first definition is that if two vertices are adjacent in a rooted tree, then we will call one vertex as parent and another vertex as child. If two vertices are adjacent in a rooted tree, then one vertex is called parent and another vertex is called child. For example, we can see here A and F are adjacent, so one vertex is parent, another vertex is child. Here also G and H are adjacent, so one vertex is parent, another vertex is child. Now which vertex is considered as parent? So the vertex which is closer to the root, the vertex which is closer to the root is considered as parent. So by default A is always a parent because A is a root and here F is child of this vertex A. These two are also adjacent, G and H. So one is parent, one is child, but the root G is the vertex G is closer to the root A as compared to this vertex H. Therefore, we will consider H as child and G as parent. So remember this terminology, that whenever two vertices are adjacent in a rooted tree, then one vertex is called parent, another vertex is called child, and the vertex which is closer to the root is a parent. So we can see that the root is always a parent of some vertex. And suppose we have only one vertex in our graph, then in that case things are different. But suppose we have at least two vertices in a rooted tree, then root is always a parent. Now the vertices may have same parent also. For example, if I consider this B, F and G, then B, F and G are adjacent with root A. Therefore, this B, F and G are children of root A. So these vertices B, F and G are having same parent. So they are called siblings. This terminology is exactly similar which we are using in English language. Siblings means the vertices having same parent are called siblings. And another terminology is leaf. Leaf means the vertex which is having no children is called leaf. So we can see here this D and E and K, L and M and I also. These vertices are not having any children, therefore they are leaf, or plural is leaves. Leaves are those vertices which are having no children. The vertices having no children are called leaves, and the vertices having at least one children are called internal vertices. Vertices that have children are called internal vertices. So here we can see the internal vertices are A is a internal vertex because it has 3 children. This B is also an internal vertex because it has children, child C. D and E are not internal vertices. Similarly, F is also not an internal vertex, it is a leaf because it has no child. G is an internal vertex, it is having a child C, I and J. H is also an internal vertex, I is not an internal vertex, it has no child, and J is internal vertex because it has 2 children, L and M. So the vertices that have children are called internal vertices. The vertices which have no children are called leaves, or singular word is leaf. And we can notice that whenever our vertex is a leaf, it will incident with only one edge. The edge meeting or ending at a leaf is only one. Therefore, leaf is defined as vertex whose degree is 1. Vertices having degree 1 are also called as leaves or leaf. So there are two definitions for leaves. The vertices having degree 1 are called leaf or leaves, and vertices that have no children are called leaves. I have written all these definitions here. They can ask you to define this type of definitions, or they can give you some rooted tree and they can ask you to identify parent, child, siblings, internal vertices, leaves, etc. So this is very easy terminology. You can easily identify all these things in a rooted tree. Another definition is ancestor of a vertex. So what is meaning of ancestor of a vertex? For example, if I am talking about ancestor of a vertex E. So what is the meaning of ancestor of a vertex E? So ancestor of a vertex E is nothing but parent of E and parent of E also, and so on. So parent of E is vertex C, parent of E is vertex B, and if we go in this direction we have up to A. So we can see ancestor of a vertex E is nothing but all the vertices in a path from root to the vertex itself. If we consider, if we are interested in the ancestor of E, then what we will do, we will find out the path between root and vertex E. That is, this is the path between root and vertex E, and all the vertices along this path excluding vertex E and including the root are C, B and A. So these are nothing but ancestors of this vertex E. This is the meaning of ancestor. So if they ask you to write down the definition of ancestor of a vertex, then you can write that ancestor of a vertex other than root. We will not talk about ancestor of a root because root is not the child of any other vertex. So the ancestor of a vertex other than root are those vertices in the path from root to the vertex itself, and including the root and excluding the vertex itself. So that I have written here, the ancestors of a vertex other than the root. That is, we will not talk about ancestor of a root. The ancestors of a vertex other than the root are the vertices in the path from the root to this vertex, and we will not consider that root, that is excluding the vertex itself and including the root. And in simple language we can say that parent of a root, parent of a root, that is grandparent, and so on until the root is reached. For example, if I am interested in the ancestors of this vertex K, then I will try to reach this root A from this vertex K, and whatever vertices I will find in that path are nothing but ancestors of K. So if we travel from this vertex to the root, then we obtain H, then we obtain G, and we obtain A. So this H, G and A are nothing but ancestors of this vertex K. So we can see H is the parent of K, G is the parent of K, that is parent of H, and A is the parent of G. So these are the ancestors of vertex K. Another definition is descendants. Descendants means, for example, if I am interested in the descendants of B, then descendants of B are this C, D and E. That is, we will go in reverse direction. Descendants of B are those vertices whose ancestor is vertex B. So B is the ancestor of D, B is the ancestor of C, and B is the ancestor of E also. So this C, D and E are descendants of B. So here we can think about child child of a child, that is grandchild, and so on, starting from this vertex. So that is another definition that I have written. The descendants of a vertex V are those vertices that have V as an ancestor. For example, this B is also an ancestor of C, D and E. So the descendants of B are C, D and E. Similarly, we can say that if we consider this path, suppose we are interested in the descendants of G, then we can see that G is an ancestor of K and H. So this H and K are descendants of G. Similarly, this J, L and M are also descendants of G. So if you are interested in the descendants, you can think of child or children of that vertex, and you can go in this direction. I consider children of G, R, H, I and J. So I is also descendant, and then I will go further whether this is having any child or not. So I will count all those children along that path. So the descendants of G, R, H, I, J, K, L, M, that is children of G, then children of G, and so on. And for ancestors, we have to consider parent of a vertex, then parent of a parent, and so on in that sense. So that is meaning of descendants. And finally, we are having this definition: subtree with some vertex as a root. Suppose we have some vertex in a tree, then subtree with that vertex is the subgraph of the tree consisting of A and its descendants and all edges incident to these descendants. If I am interested in the subtree with some vertex as its root, then I have to consider the subgraph of the tree in which we have that vertex A and its descendants and all edges incident to these descendants. So here we can see that if we consider this portion, suppose I am interested in a subtree with G as its root, then I can consider this whole portion. All these are descendants of G. So this part is a subtree. This part is a subtree with G as its root. So subtree with a root is the subgraph of a tree in which we include G and all its descendants and with all edges which are joining all these descendants. Similarly, we can consider another subtree in which we consider B as a root. So this is the subtree with B as a root in which we have taken B and all its descendants and all edges incident with B. So that is meaning of subtree with a root. So remember all this terminology, and we will continue with this type of terminology or concepts related to trees in upcoming lectures. Thanks for watching.